Section 2.1 Factoring and Simplifying Rational Expressions. The objectives are to review multiplying and factoring polynomials and review simplifying rational expressions and algebraic fractions involving radicals. We begin by multiplying polynomials. To multiply polynomials, we will need to know the distributive property, which tells us what to do if we have a factor in front of a parentheses with a sum inside. The property basically says multiply the factor on the outside with everyone inside the parentheses. We can generalize this to multiply a binomial with a second binomial using what's known as the FOIL method, where you multiply the first, then the outer, then the inner, then the last terms in the two binomials. So let's review how to do this with example number 1. Example number 1 says multiply each set of polynomials. So first we have x plus 5. And we're supposed to multiply that with the 2x plus 3. So first things first, we'll grab the x from the first polynomial, or the first binomial, and multiply it with the 2x. That represents the f part of FOIL. Then we multiply the x with the 3. That represents the o. So this is f, this is o. Next, we will grab the plus 5 and multiply with the 2x. And finally, the 5 with the 3. And those represents the I and the L part of FOIL. So x times 2x will be 2x squared. X times 3 will be 3x. Then 5 times 2x will be 10x. And finally, 5 times 3 will be positive 15. This is the end of the product, but we typically have to simplify the polynomial and add any like terms. So in this case, we add the two middle terms to end up with 2x squared plus 13x plus 15 as the final solution. Okay, so let's do this again one more time with the 3x minus 2 multiplied with 5x plus 7. Take a second to pause the video and see if you can get the answer on your own before we write it together. Okay, so 3x minus 2 multiplied by 5x plus 7. Again, we will use the same pattern. Multiply the 3x in the first parentheses with the 5x, then multiply the 3x with the 7. And next, we grab the negative 2, multiply with the 5x, then multiply that with the 7. So 3x times 5x will be 15x squared. 3x times 7 will be 21x. Negative 2 times 5x will be negative 10x. And finally, negative 2 times 7 will be negative 14. And as before, we will add the middle terms. The middle terms are considered like terms because they both have x to the power of 1. Even though the 1 is invisible, we know it's there, it's not written. And so we end up with 15x squared plus 11x minus 14. This ends our discussion and review on how to multiply polynomials. So now what we want to do is review how to factor polynomials, and the process is a little bit more involved, but basically the idea is, what if I give you this answer that's in the box and I want you to go backwards? That process is what we call in math factoring. So there are different methods for factoring, and there are different techniques for factoring depending on the number of terms that you have in the problem. So if you have 2 terms versus 3, 4, or more, you will apply a different strategy. The procedures are all listed in this table, so take a second to write them down or screenshot this, but what we will do on the next few pages is go through all these different strategies. And again, the idea is to turn a sum of terms into a product of 2 binomials or more. There are some interesting formulas right here in the middle of the table. Those are special formulas that we use when we have difference of squares or difference of cubes or sum of cubes. Notice how that the sum of the 2 squares does not factor. This is a prime, and the word prime indicates that a polynomial cannot be factored. Okay, so let's go ahead and practice some of these methods, beginning with factoring out the GCF. The GCF is known as the greatest common factor. And one of the basic tricks for factoring is to recognize the greatest common factor and factor out of a polynomial. So how do we factor out the GCF? What is the GCF? As we mentioned, it's the greatest common factor. And the steps for finding the GCF are all listed in this first half of the table. I'll give you a second to pause the video, read them, write them, take a screenshot, whatever you want. And so in example 2, we are told to factor the given polynomial. Sometimes they'll say the word factor completely. Does not matter what it says. We will begin with the same strategy, with the same process always, which is first write the problem down so you can recognize what you're dealing with. Then the next thing you want to do is count the number of terms that you can find in your problem. So in my problem, I've got 1, 2, and 3 terms. So terms begin and end where there's a plus sign. So there's a plus sign right here, so that's the beginning and end of the first term and second term, and then so on till you reach the end. The first thing I'm going to focus on is the 15, the 5, and the 20. Do they have any common factors? It may be obvious to you that all of these numbers have a common factor. They are all multiples of 5. For example, 5 times 3 is 15, 5 times 1 is 5, and 5 times 5 times 4 is 20. So that means that my GCF should contain at least the number 5, because 5 is a factor that goes evenly into all of these highlighted numbers. The next thing we'll do is focus on the letters. In this case, I'm going to start with the y. And it seems like all of my 3 terms have a y term in them. So that means my GCF should contain the variable y. And according to the steps above in the table, the y that you pick will be the smallest power that you can find in the problem. So in this case, I have power 2, then power 7, then power 3. The smallest power I can find is the power 2, so my GCF is going to be 5y squared so far. And finally, I'm going to look at the other variables. There is a z that we can find in all of these terms. So my GCF will contain the variable z. And since all of them have power 1, that means the z that I'm going to factor out is going to be also z to the power of 1. Okay, so then once we find the GCF, we go ahead and write it first. And the question now is, what should be written inside the parentheses? So the answer is going to be the quantity that needs to be multiplied by 5y squared to give me the original 15y squared z. And so in this case, all I have to do is multiply the 5 with the 3, and I'll end up with 15y squared z, which is the original first quantity that was there, or the original first term. So I'm done with the first term. Next, moving on, 5y squared z times what will give me back 5y to the power of 7 with the z. So the 5 is accounted for, the z is accounted for, but we only have 2 y's on the outside, and we would want 7, so that means we're missing 5 y's. So y to the power of 5 is going to be the middle term. And finally, the last term, 5y squared z times what will be the original third term. And so 5 times 4 seems like it's going to be 20. I've got y squared on the outside, but I need to have y cubed, so that means I'm missing a letter y. And finally, the z is just going to carry over. When I multiply the 5y squared z with the 4y, I'm going to end up with the original third term that was already there. And so this is the end. Now, it may be confusing for some people to find the 3 and the y5 and so on. So here's an alternate method. To find the 3, what you could do is take the original first factor, which was 15y squared and z, and divide it out by the GCF. So if I divide it out by the GCF, you'll realize, or you'll notice, that some terms are going to get canceled out. The z's are going to cancel out, the y squared are going to cancel out, and 15 divided by 5 will be 3. And as you can see, the number that we wrote was 3. So if I do this again one more time for the second term, what would I get? So I want to know what to place inside of the middle term. So how can I determine that? I take the original second term, which was 5y7z, and I divide it out by the GCF, which is 5y squared and z. And if I do this, the 5's will cancel out, the z's will cancel out, and we end up with y7 divided by y squared. So that means there's 7 y's on the numerator, there's 2 of them on the denominator, we can cancel 2 and 2, and that leaves us with y5, and that in turn is the new middle term. You can check that the third one will be also 4y. I'll leave that to you. So let's try this one more time. We have next 8x plus 16 minus xy minus 2y. So here we have 4 terms in this problem. And the first term is 8x, the second one is 16, then negative x, then negative 2y. So let's begin by writing it down. And notice what we need to do as we write it down. So there are 4 terms. When your problem contains 4 terms, typically it's difficult to find a common factor for all 4 of them. So what we will do is use a method called grouping. So we're going to kind of think of these two as being like together and these two being together and ask, what does 8x and 16 have in common? So their GCF is going to be 8 because 8 times 1 will be 8 and 8 times 2 will be 16. So we take 8 and then we write the missing factors. So 8 times what will be the original 8x? I need x. 8 times what will be the original 16? I need basically 2. So that's basically the end of the first part of the problem, the first group. And now we look at the second group. So what's going on with the second group? What do you notice that is common there? Well, I've got a negative xy and I've got a negative 2y. So at least I can see they both have a negative. That's common. And the letter y repeats in the first factor and also the second factor. So we're going to factor that GCF out. And if we factor negative y out, what will be left inside of the group? What will be left inside of the factors? Well, negative y times x will give me back the original negative xy, and negative y times positive 2 will give me back the original negative 2y. So there we go. We've factored the problem so far in using the grouping method. And now we are going to look at the new answer and ask ourselves, are there repeating factors? So this time we can think of the 8x plus 2 as being one term and the negative yx plus 2 as being the other term. And what's common to both of them is the term or the factor x plus 2. So what we'll do is we'll grab the x plus 2 and write it first. And once you write it first, the next thing you'll do is open up a set of parentheses and write the leftovers. So if I remove the x plus 2 from here, what will be left over? Well, what will be left over is just the 8. And if I remove the x plus 2 from the second factor, what will be left is the negative y. And so this is it. We've turned the original sum and difference of terms into a product. There's nothing between the parentheses. That implies automatically that it's a product. And this is the factor form of this polynomial that contains 4 terms. Okay, so now we turn our attention to factoring a trinomial. So what is a trinomial? A trinomial is a polynomial containing 3 terms, such as x squared plus 5x plus 6. There are 2 types of trinomials that we'll care about in this particular review. Polynomials where the leading coefficient, meaning the number next to x squared, is 1, and polynomials where the number is not equal to 1. The procedure is written right there, so pause the video and write it down or screenshot it, but I'll explain how it's done with the problems below. Now I'm going to be using something that I like to call the big X methods. However, this is not the technical term. It's actually known as the sum product method, but I like calling it the big X because it reminds students instantly what they're supposed to do when they see a trinomial. So the first thing that we're going to do is look at example 3 with part 1. We've got 6x cubed plus 12x squared minus 90x. This is an example of a trinomial, and no matter what kind of problem you're given, the first thing you want to check is, can I use the GCF method? Can I factor anything out of the 6x cubed, the 24x, and the 90? If it's possible, then you should do it. If it's not possible, then you move on to the next step. And in this particular problem, I should be able to find a common factor for the 6x cubed, 12x squared, and 90x. The common factor that I clearly can see is a 6 and an x, because 6 times 1 will be 6, 6 times 2 will be 12, and 6 times 15 will be 90. and I also see x cubed, x squared, and an x to the power of 1. So I grab the x with the lowest power, which gives me x to the power of 1 in my GCF. So since that's a GCF, we write it first, and once we write it, we will copy the missing terms. So 6x times what will be the original 6x cubed? Well, I need just simply x squared. Next, 6x times what will be the original 12x squared? I'm going to need to put 2x in here. And finally, 6x times what will be the original negative 90x? Seems like we need negative 15. 15 times 6 will be the negative 90. So once we've done that, it is time to focus on the trinomial x squared plus 2x minus 15. This is where I'm going to use this big X method thing. So what I'm going to do is draw a little diagram on the side. I'm going to first check that there's a 1 in front of x squared, which is great. There's a 1 there, so that means we are going to be able to use some shortcuts. I grab the negative 15 from the end, I multiply with the 1, and I write the answer on top of my diagram. So negative 15 goes on top. Then I grab the positive 2x from the middle, and I write it on the bottom of the diagram. And then I ask myself the following question. Can I find two numbers whose product will be negative 15, but whose sum is going to be 2? So I'm looking for two numbers, 3 and 5, for example, or 1 and 15, for example, or negative 1 times negative 15, for example. I want the product of the numbers to be this number on top, negative 15. So obviously 3 and 5 won't work because I need a negative 15 there. But not only that, I want their product to be negative 15, but I want them to add up to the number 2. So if you can find such numbers, then great. And in this case, yes, we can find such numbers. The numbers that we are looking for are going to be negative 3 and positive 5. So you can check it to yourself. Negative 3 multiplied with positive 5 will be negative 15. And when I add negative 3 and 5 together, I get the positive 2 that was already on the bottom. So what I do next is basically write down the 6x, and since I had a leading coefficient of 1 in front of the x squared, we can simply factor the problem completely by writing x, which is the variable of the problem, and then copying the numbers that we just found in our diagram next to it. And this is the end. Now, if the number is not 1 in front of the x squared, there will be some intermediate steps in between these two lines. We would have to do extra work, and that's what we're going to demonstrate in the next part of this problem, where we have the 3x squared plus 14x minus 15. So copying the problem down, and as you copy it, you want to start thinking, what am I dealing with? How many terms are there? This problem has only 3 terms, and there's nothing common between the 3, 14, and 5. So unfortunately, we can't use the GCF method. So we go to do the next best thing, which is that big X method. So to set up, I grab the 3 from the beginning and the negative 5 from the end, and I multiply them. The answer is going to be negative 15. Then what I do is I grab the 14 from the middle and I put it on the bottom of the diagram. Okay, so the question is, can we find two numbers whose product is negative 15 but whose sum is going to be 14? So you can think of numbers that multiply to 15, but we want it to be negative 15, so maybe negative 1 or maybe 1 and negative 15. You can think 3 and 5. If you make the negative 3, that will work. Or you can make 3 and negative 5. That will multiply to be negative 15. And you can go through the list to see which one of those pairs will have a sum of 14. So if I add negative 1 and 15, I get lucky because the sum is going to be 14. So that's awesome. The numbers I need are negative 1 and 15. And always double check it once you write them down. Multiply the numbers, negative 1 and 15, and see if you end up with the top value. Add them up and see if you end up with the bottom value. Unfortunately, though, the leading coefficient in this problem is 3, not a 1, so this means we have to go through some middle steps. So we'll write down the 3x squared. From this point on, we will not write the 14x. Instead, we will write negative 1x and positive 15x instead of the 14. Keep in mind that when you add these guys up, it will be the 14. So we're just rewriting the problem without the 14, but turning into two different terms. And finally, we put the negative 5. So we took a problem that had 3 terms and turned it into a problem that has 4 terms. And what we will do next is group each two together and think about what they have in common. So ignore the 15x and 5 for a moment. Look at the 3x squared and negative 1x. What's common to both of them is just simply x. So we factor out the x, and that leaves us with 3x minus 1 inside the parentheses. Now we turn our attention to the 15x and 5. What's common to both of those? 15 and 5 are both multiples of 5, and so we factor out the 5, and that leaves us with 3x minus 1 to go inside the parentheses. And now we're thinking of this x times 3x minus 1 as one unit, and we're thinking of the 5, 3x minus 1 as the other unit or the other factor. What is common there is the parentheses that contains 3x minus 1. So we grab it and we write it first. And once we finish writing it, we put all the leftovers inside of the second parentheses. So in this case, the leftovers are x plus 5. And that is the end of the whole process. We need to box it, and we're done. So as you can see, it's slightly more challenging when the leading coefficient is not equal to 1. You'll have to do extra steps, but it's not too difficult. Now let's move on to example 4, where the question again is to factor each polynomial. However, this time we're dealing with 2-term polynomials. So in this case, we're dealing with 49x squared minus 36y squared. And right off the bat, I don't see anything common to the 49 and the 36 or the x squared with the y squared. So maybe there's a special pattern. And on the first page of this handout, we have some formulas, and one of them is called the difference of squares. The formula is a squared minus b squared is supposed to be factorable, and it factors into a minus b times a plus b. So if you have a base that is squared and another base squared with a minus in the middle, you can directly factor it out using this formula. And so in my case, it seems like I have some 2 bases being squared. As a matter of fact, 49x squared is the base 7x being squared, and the 36y squared is the base 6y being squared. So it kind of looks like the pattern that we were describing, where for me, a is really 7x and b is really 6y. So all I have to do now is follow the formula or the pattern to finish up the problem. So according to the formula, I'm supposed to have 2 parentheses. One of them will have a minus and another one will have a plus. And all we got to do is write down 7x in the first half of each parentheses, and then write down 6y in the second half of the parentheses. Now, I ended up putting 7x minus 6y first, but you can put 7x plus 6y first. As long as the other parentheses will have the minus, you will be okay. So there are 2 possible ways of writing down the solution, depending on which one you want to put first. Both of these are equivalent, though. Something similar is going to happen in the next 2 parts, except the formula is going to be a little bit different. Again, we're dealing with 2 terms on this part 2 of the problem, and we have 8x cubed minus 125. Again, there's nothing common to the 8 and the 125, but I can see that 8x cubed is some kind of base, actually 2x cubed, and I can see that the 125 is the base 5 cubed. So in other terms, if I do 5 cubed, I get 125. And so this pattern reminds me of another formula that we had on the first page, which is the a cubed minus b cubed formula. And the formula needs to be memorized. Nobody's going to tell you this on an exam or a quiz. You need to know it. The formula says that a cubed minus b cubed is a minus b times a squared plus ab plus b squared. So in my case, the a is 2x and the b is 5. So a is 2x because that's the first base that was cubed, and the b is the 5 because that was the second base being cubed. So what I have to do is basically replace all the a's with 2x and all the b's with 5 to get my solution. So there's going to be a tiny parentheses followed by a really big parentheses with a lot of terms inside of it. And the first parentheses contains just simply 2x and 5 with a minus sign in the middle. That's what the formula tells me to do. The second parentheses asks me to first square the a. So I'm going to take the 2x and square it. Then the formula tells me to put a plus sign, then multiply the a and b with one another. So I'm going to multiply the 2x and the 5 with each other. And finally, it tells me to write down a plus and a b squared. Now keep in mind the b is 5. So if you know that 5 squared is going to be 25, you can write that already, but I'm just going to put 5 squared for now. We're almost finished. All we have to do now is clean up this mess a little bit. So 2x minus 5 is going to go for the right. 2x squared is going to be 4x squared. 2x times 5 is going to be 10x. And finally, 5 squared is going to be 25. And that is the end. Now, you don't have to waste your time checking if this part of the problem factors. If it was factorable, the formula would have done it for us already. So the 4x squared plus 10x plus 25 is going to be what's called prime, so it does not factor any further. But this is enough because we already have a multiplication in the middle with the two factors 2x minus 5 and the second trinomial for x squared plus 10x plus 25. So we have answered the question in this problem. Okay, last part of this deals with the 27a squared and then 64a squared b cubed. So we're dealing with two terms. And again, the first thing I'm going to do is check if there's anything common between the terms. So use the GCF method. And I can see right off the bat that there is a GCF. As a matter of fact, the letter A is being repeated in both of my terms. And the smallest power I see is the power 2, so I just grab it and write it first. Will be on the outside, and what's left inside the parentheses will be 27 minus 64b cubed. So I factor out the GCF, which is a squared, and that leaves me with 27 and 64b cubed. And those guys in turn look like a pattern. The 27, as a matter of fact, is the cube of 3. So let's record that. 3 cubed is going to be 27. And actually, 64b cubed is the cube of 4b. So the quantity for b, when cubed, will be 64b cubed. And again, this is a difference of cubes. So again, we can use the formula like we did in the previous problem to write down a squared on the outside, then the 3 minus 4b. Then we will have to square the 3, put a plus sign, multiply the 3 with the 4b, and finally we need to square the 4b quantity. And once we do that, we'll be completely done. So a squared, 3 minus 4b is the second factor. Then the third factor will be 3 squared, which is 9, plus 3 times 4b is going to be 12b. And finally, 4b squared will be 16b squared. So this is the final answer, and we are completely done with the problem. The next topic that we have to review is rational expressions. So first of all, what is a rational expression? It is a fraction that contains a polynomial on the numerator and a polynomial on the denominator. So it has the form of p over q, where p and q are both polynomials, and remember that the denominator cannot be equal to 0. And the first thing we will talk about is how to simplify these expressions. And to simplify rational expressions, what you want to do is factor the numerator completely, factor the denominator completely, then cancel out any common terms that you can see. We already did a couple times in the previous examples on small fractions, but we will try to do it again with these more complicated ones. So first, example 5, it says, simplify each of the following rational expressions by dividing out any common factors. Sometimes you'll just see the word simplify and not any of this rest of the question. So you'll know that you're dealing with a rational expression, 3x minus 12, for instance, divided by x squared minus 16. And to simplify it, we want to factor each of the numerator and denominator using any of the methods that you know. In this first one, the numerator is 3x minus 12. The GCF there is supposed to be 3. And so I'm going to factor 3 out, and that leaves me with x minus 4 within the parentheses. Because 3 times x will be 3x, and 3 times negative 4 will be the original negative 12. On the denominator, I have x squared minus 16, which reminds me of the difference of squares. This reminds me of x raised to the power of 2 and 4 raised to the power of 2. And because it's a difference of squares, I can write it as x minus 4 multiplied by x plus 4. So I'll put that on the denominator. So x minus 4 multiplied by x plus 4. And now the numerator is completely factored. There's a multiplication between the 3 and the factor, and the denominator is completely factored. I can see that the same parentheses, x minus 4, is repeating on the numerator and the denominator. So I erase it and I write a 1 in its place. So that means it's going to be 3 times 1 on the numerator divided by 1 times x plus 4 on the denominator. And those extra 1s are not going to make any difference. 3 times 1 is 3. And 1 times x plus 4 is simply x plus 4. And that's how you factor and reduce the fraction. Okay, in part 2 of this problem, I have 7 minus y on the numerator, and I have y minus 7 on the denominator. The terms look almost the same. There's a plus 7 on top. It's an invisible plus sign, but it's plus nonetheless. But the 7 has a minus on the denominator. And the y term on the numerator has a minus, but the y on the denominator has a plus sign. So what to do? Well, if I can factor a minus sign from either the numerator or the denominator, then I'll be able to reduce the fraction. And just simply because we have a negative in front of this y, I'm going to factor a negative 1 from the numerator. And I'm going to leave the denominator just alone. I'm just going to keep it as y minus 7. Now, negative 1 times what will be the original positive 7 that was already there? Well, negative 1 times negative 7 will be the original 7. And so I'm done with the first factor. Now, negative 1 times what will be the original negative y that was there? And I will need to put a plus y because negative 1 times positive y will be negative y. However, I don't like how this parentheses on the numerator is written. So it's usually more common to write the variable first, then the number. And because the y has a positive, I don't need to write down the plus sign. I could just write simply y minus 7. And so now you can see that the quantity y minus 7 is repeating, so we can finally remove it. And when we remove it, we end up with just 1 in its place because it's being reduced. And negative 1 times 1 divided by 1 is just simply negative 1. So that's how you would factor that numerator, and you would reduce the denominator. So in general, if your variable has a minus sign, it's a good idea to factor a negative 1 out. Okay, for part 3, we have a slightly more complicated expression with the 3x squared minus 5x minus 2. All divided by 4x squared minus 16. So right off the bat, the 3x squared minus 5x minus 2 looks complicated. I'm going to need to factor it, so let me do that on a scratch paper on the side. It's a trinomial with nothing common between all the factors. So because nothing is common between all the factors, let's go ahead and try the big X method. So my big X method will contain the 3 times negative 2, which is negative 6 on the top of the diagram, and it will contain -5 on the bottom of the diagram. So the question is, can we find two numbers that multiply to -6 whose sum is -5? And the answer should be yes. Maybe you have already thought about -1 multiplied with, -6 multiplied by +1. If you thought about that, that's great. Then now we will just need to write down 3x squared minus the 6x plus the 1x minus 2. If you're wondering whether the 1 needs to be written down here, the answer is not really. You could just write x if you like, or if you like to put the 1 there, it's not a problem. It's up to you. Now, the first 3x squared minus 6x will have a common factor, which is the 3x. When I factor it out, I get x minus 2. And the second two factors, x minus 2, have nothing in common, but we can always write a plus 1 and just put parentheses x minus 2 there. Now, we have 3x multiplied with x minus 2, and we have 1 multiplied with x minus 2. So that means we can write x minus 2 in front because it's repeating, and put the 3x plus 1 next to it. So the x minus 2 is repeating. We write it first. And whatever else is left over, the 3x, the 1, we put them inside their own parentheses. So my numerator is now completely factored. I'm just going back to the main problem and writing down the answer for the factored version of the numerator. Now the denominator, I have 4x squared minus 16, and those two terms, believe it or not, have a common factor. As a matter of fact, it's a 4, because 4 times x squared will be 4x squared, 4 times 4 will be 16. So there, I can write 4, then I can write x squared minus 16. However, x squared minus 16 itself is a difference of squares, so I can factor that part itself and use the difference of squares pattern or formula to rewrite it as x minus 4 times x. I meant to say 4, not 16, which means it should be x minus 2, x plus 2 on the denominator. I made a typo. 4 times 4 will be the 16. I copied the 16 right off the bat without changing it, but it should be 4 instead. And still, it is a difference of squares with x minus 2, x plus 2 as the result. But now I can cancel out the x minus 2's, and the final answer will be 3x plus 1 on the numerator divided by 4 multiplied with x plus 2 on the denominator. And if you're wondering, should I multiply the 4 to the x plus 2? The answer is no, leave it alone. We don't care to multiply it out. We spend so much time and effort to try to factor it, so let's leave it in the factored form. Okay, again, we have another one to deal with, x squared minus 4x, all divided by 3x squared minus 11x minus 4. So I recommend that you try to pause the video here and see if you can solve it on your own, see if you can factor it out. For the numerator, you'll need to use the GCF method. For the denominator, you'll need to use the big X method. Okay, so I factored the denominator portion, and let's try to work out the numerator by itself. So x squared minus 4x, the GCF there consists of the variable x. So if I factor out the x, what would be left is just simply x minus 4. And so now let's take everything back and put it into the original problem. So we had x minus 4 in the numerator. It was multiplied by the original x, the GCF. The denominator got factored using this big X method. And let me shrink all this down a little bit so we can have some space. But the idea is the denominator will have x minus 4 and the 3x plus 1 that we found on the scratch paper. And as we can see, now it's a product on the numerator, it's a product on the denominator, so we can divide out the x minus 4's. And from this point on, I'm not going to write the 1's anymore. I'm just going to multiply it in my head. So x times 1 is just going to be x. 1 times the 3x plus 1 will be just simply 3x plus 1. And that is the final answer there. So did you get the same thing? If you did, awesome, great. If not, talk to me in office hours or shoot me an email and let's see why you're not able to do this. This is supposed to be a little bit of a review. So that's why I'm going a little bit fast on this part of the section. Now, one thing we did not address with these two problems that we just finished doing is the complex rational expression situation. So first of all, what's a complex rational expression? It's basically a fraction where the numerator and the denominator consist of fractions themselves. So you may have things like this example here, where the numerator has the fractions 3 over y plus 5 and 3 over 5, and the denominator may or may not have fractions. In this case, it does have y, which is the same thing as y over 1. So how do you simplify these things? One of the easiest methods to simplify these types of complex fractions is to multiply the numerator and the denominator by the LCD of every denominator that you see. So let's illustrate by going through this example 6, which has 3 over y plus 5 minus 3 over 5, all divided by y. And just for clarity, I'll add the 1 underneath. Even though y doesn't have a 1, I'm going to add it. And what I'm going to do next is look at the y plus 5, the denominator, and the 5, the denominator, and the 1, and ask myself, what would be the LCD for all of those? LCD stands for least common denominator. So I want a denominator that contains within it the y plus 5, the 5, and the 1. And that LCD will just simply be y plus 5 multiplied by 5. So what I'll do next is I'll take everyone on the numerator and everyone on the denominator, and I'll multiply them by this y plus 5 times 5 quantity. So again, take everyone there, the 3, the y plus 5, and multiply it by the LCD, which is 5y plus 5. And do the same thing on the second fraction. It used to be 3 over 5. I'm going to give it the quantity 5y plus 5. And finally, the original y that was on the denominator, I'm going to multiply it with 5 and y plus 5. Now remember, these extra quantities we're adding are all divided by 1. I'm not going to add all those extra ones because then it will be confusing. So I'll erase them in a few seconds. But what I want to emphasize is the fact that when you multiply any fractions in this particular problem, some things should happen, some things should reduce. We're not going to actually FOIL everything. So for example, the y plus 5 and the y plus 5 will cancel out. The 5 and the 5 will cancel out. And unfortunately for the denominator, nothing cancels out, so we'll not worry about it too much. So when you cancel things out, what is going to be left over? So for the numerator, as we just mentioned, the y plus 5s are going to disappear. You'll be left with 1, 1, 5, and 3. So you'll multiply the 3, 5, and 1, and that's going to be 15. But 15 divided by 1 is the same thing as 15, so let's just write down 15 instead. Okay, so that's how that first one is done. Next, we said we can cancel the 5s, and what's left on that second half is the negative is going to remain. The 3 times 1 will be 3, divided by 1 times 1 is just going to be 3, and the extra y plus 5 is going to come down. It's not going to be reduced on this particular fraction. Finally, at the bottom, on the denominator, nothing will actually cancel out. So what we do is we just go straight across. We multiply at the top with the top, the bottom with the bottom. So numerator goes with numerator, denominator goes with the denominator. And so it's going to be 5y and y plus 5. And 1 times 1 is just going to be 1. But again, I'm not going to write divide by 1 because it's not going to make any difference. Okay, so be careful not to cancel the y plus 5 and the y plus 5. We cannot do that in this case because of the minus in the middle. That prevents us from reducing the fraction. It's not a factored form, so we cannot reduce anything. What we could do instead, though, is try to FOIL the numerator and the denominator and add like terms and see what happens afterwards. So for example, in this particular problem, I've got 15 minus 3y, so it's going to be 15 minus 3y, and then I've got negative 3 times 5. That's going to be another negative 15 at the end. On the denominator, it's nice and pretty, already factored, so just leave it alone. Our goal is to cancel things, So it's better for us if it stays factored, because then we can reduce some terms if they repeat. And as you can see, the numerator 15 minus 15, they're like terms, so they just add up to 0. And so far, I have negative 3y on the numerator, and I have 5y and y plus 5 on the denominator. There's multiplication everywhere between the 3 and the y, between the 5y and the y plus 5. And so I can now get rid of the y's and reduce them to lowest terms. So my final answer will become negative 3 divided by 5 with y plus 5 inside parentheses. And like I said before, it's better for us to leave it factored just in case we don't know what we're doing with the problem later on. And having it factored is more convenient than foiling the denominator. Okay, for part 2, the situation is slightly more complicated because I don't really have any numbers. It's just all variables, but we proceed the same way. I'm going to start by writing down the original problem, 1 over x plus h minus 1 over x, all divided by the h. And you can think of this h on the denominator as having 1 underneath it. Does not matter if you do that or not. But in any case, we have the first denominator x plus h, we have x, and then we have 1. What's the LCD for all those? So the LCD for all those will consist of 1 and x plus h, which is just x times x plus h when you multiply it all together. So we're going to take this LCD that we just wrote, and we will need to multiply every fraction in the problem, every term in the problem with this LCD. So in other terms, the first fraction, 1 over x plus h, will have next to it an x times x plus h. The 1 over x that was already there is going to get another x times x plus h. And finally, the denominator that used to be h over 1 will end up with another x plus h next to it. So remember, these guys are showing up because they are the LCD, and this is just one strategy to reduce complex fractions. So we multiply the LCD by every fraction that used to be there, or every term that used to be there. And although I'm not writing the ones underneath all these LCDs, you should realize that there's an invisible 1 there, so be careful when you're multiplying things out. You always go straight across, top with top, bottom with bottom. But before you multiply any expressions, you should always think, can I reduce the expressions first? So for instance, on the x plus h and x plus h, we can reduce, and what's left from all of this mess is just 1 and x and 1 again. So multiplying and dividing all those things, we just end up with x. Now moving on to the second term, there's a minus already there, so make sure you record it and cancel out the x term this time. That's the only thing that repeats. And that leaves us with another parentheses that contains x plus h. And finally, the denominator, unfortunately, nothing cancels out, so we're just going to write x times h times the parentheses x plus h. Now, be careful again. Do not cancel out the x plus h's. That's not legal. That's not allowed because of the big old minus sign in the middle. So what you want to do instead is distribute this minus sign to the parentheses, add like terms, and see what happens. So if I distribute the the negative, I get negative x and negative h. And the denominator is still the same, x, h, or hx. And then finally, the parentheses x plus h. Seems like this x and this negative x will cancel out. And what I'll have is a negative h on the numerator and hx with the quantity x plus h inside the parentheses. Now, since all of these guys are being multiplied with each other, we can finally remove the h from the numerator and the denominator and reduce it to 1. And so the final answer will be a negative 1 on the numerator with x times x plus h next to it on the denominator. And that's it. Okay, the last thing we will talk about is how to deal with radicals. This will be helpful in the future when we're looking for limits. So the idea is if your fraction contains radicals, sometimes the radical's on the denominator and we don't like that. So what we will do is we will multiply by the conjugate. The conjugate of a quantity, square root of a plus square root of b, is square root of a minus square root of b. So the conjugate basically flips the sign in the middle from negative to positive, or if it was already negative, it makes it positive. If it was positive, it makes it negative. And so typically speaking, when you do this, it's during the process of what we call finding the limit. But for now, we don't have limits. We don't know what that is. So for now, we'll just kind of practice how to do this process with some random numbers, in this case 3 plus square root of x divided by 9 minus x. The question here will be to use multiplication by the conjugate to rewrite each of the following fractions. In the future, the question will be different. It will be just find the limit of something, and then your expression will have some kind of radical in it, and you'll have to remove the square root. So anyway, in this particular problem, I'm going to look for the term that has the radical. It's this one, the 3 plus the square root of x. And what I'll do is I'll multiply the numerator and denominator both this time with the conjugate of 3 plus the square root of x. So because it was positive, the conjugate will be 3 minus the square root of x. And because I'm doing it to the numerator, it's going to change the whole expression. So to keep everything balanced, we do the same thing on the denominator. We multiply by the same exact quantity. And so the idea is this should help us avoid the square root on the numerator. So to multiply everything out, we can multiply the 3 with the 3 with the square root of x, then the square root of x with the 3, and then finally the square root of x with the negative square root of x using the FOIL method. If you recognize that this is a pattern, 3 plus square root of x, 3 minus square root of x is a pattern, then great, you can use a shortcut to do this problem a little bit faster. If you don't recognize that this is a pattern, not a big deal, but the pattern is basically telling us that we're multiplying an a plus b with an a minus b, so the result should be a squared minus b squared. And that's why we multiply by the conjugate, because when you square the square root of x here on the second term, it will disappear. Now, if you don't know the pattern or if you didn't recognize it for this particular problem, it's not a huge problem, it's not a huge issue. You could get the same result by just multiplying the 3 with the 3, that's going to be 9. Then the 3 with the square root of x, that's going to be negative 3 square root of x. Then x with the 3, that's going to give us 3 square root of x. And finally, negative square root of x will be negative x, because square root of x will become squared, and that just gives x back. On the denominator, as usual, don't FOIL anything out. It's going to be better to leave it factored for a moment. And notice what will happen on the numerator. Those middle terms are going to cancel out. And whatever's left is just 9 minus x. If you want, you can put parentheses around it. And on the denominator, we already have 9 minus x, and we already have the 3 minus square root of x. The beautiful thing here is that this and this factor 9 minus x will be reduced, and the final solution will contain 1 over 3 minus square root of x. So, like I said, this process is going to be useful later on when we're looking for limits. For now, we don't have any limits, so this is the end. But later on, we'll see that this is a process that will be very useful when you're looking for the limits of expressions, and the square root typically is going to be on the denominator, and that's why this is useful. Okay, last but not least is this expression with the square root of x plus h minus square root of x, all divided by h. So just like we did before, I'll write it down before I start solving. Put the equal sign, and I'm going to identify that the square root of x plus h minus the square root of x is on the numerator. It needs a conjugate. So whatever the conjugate is, in this case, because I have a minus sign, I'll multiply by the same quantity. But instead of a minus in the middle, I'll be putting a plus in the middle. And whatever you do on the numerator, just do the same exact thing on the denominator. Now, I'm going to use the pattern a minus b and then a plus b to FOIL the numerators very quickly. So because the pattern a minus b times a plus b gives me a squared minus b squared, I'll take advantage of that and write down the square of the a. So my a is x plus h. I want to take the square of that. My pattern tells me to put minus and then square the b. And my b is just square root of x. The denominator, we'll just copy it, h square root of x plus h minus, plus the square root of x. So we're just copying the denominator, and now let's see. The square root and the square will give me just x plus h. And again, the square root of x squared will just give me x, all divided by the same denominator as before. Now what I'll do is I'll cancel out the negative x with the positive x. So therefore, I'm going to have h on the top, and h, the square root of x plus h, plus the square root of x within parentheses on the denominator. And lastly, we will just remove the h's by dividing them out. And my final answer should look something like 1 over the square root of the quantity x plus h plus the square root of x. And this is the end of this section.